The world seems colourful to us. But in reality, it is colourless. The human eye can see only light. But again, light has no colour either. So what then is colour? Electromagnetic waves have only two parameters, length and amplitude. Electromagnetic waves do not have colour. The entire range of electromagnetic waves of different lengths is called the spectrum. Only the waves of a small fragment of the spectrum are perceived by the cells of the human eye. This portion is called light, and its image is called the visible spectrum. While a light beam can consist of a wave with one length and amplitude, for example a laser light, it can also be a mixture of many waves of different lengths and amplitudes, for example an incandescent light or sunlight. The spectral composition of light is presented by the spectral power distribution curve, which indicates the energy of waves of different lengths. On the rear wall of the human eye is the retina, which is composed of two types of light-sensitive cells, rods and cones. Cone cells are sensitive primarily to wavelengths of greater amplitude. There are three groups of cone cell types: S, short, M, middle, and L, long, which respond to three ranges of wavelengths. The sensation we experience, depending on the wavelength of light, is called a hue. When the cones are exposed to light, each of the three types of cone cells sends signals to the brain evoking the sensation of a hue corresponding to the wave amplitude. L cone cells: R hue, red. M cone cells: G hue, green. S cone cells: B hue, blue. These hues are called the primary hues. Rods are cells which are very sensitive to amplitude changes in waves of different lengths and of low energies. They are responsible for scotopic vision, i.e., vision in very dim light. They allow us to see the shapes of objects in deep darkness, yet we are still unable to see their colours. Brightness is a sensation that depends on light wave amplitude. The samples produce sensations of the same hue, though varying in brightness. When the three signals from each type of cone cell reach the brain, they produce the sensation of a certain hue and brightness. The combined set of such signals, the stimuli, is called tristimulus. If light waves stimulate two types of cone cells to the same extent, then the signals which they send are combined to produce the sensation of a secondary hue. Secondary hues include cyan, C, yellow, Y, and magenta, M. The sensations of secondary hues depend on the ratio of impulses sent by three types of cone cells. The hues produced from the combination of impulses coming from two types of cones create the sensation of pure hues. The sensation of secondary hues may be the result of various wavelengths stimulating the groups of cone cells, or the result of one light wave stimulating different groups of cones to the same extent. Therefore, each hue, with one exception, corresponds to a light spectrum wave of a certain length. Sensation of the same hue can be the result of the activity of light with varied spectral composition. Only magenta is not included in the spectrum. Secondary hues are the result of mixing adjacent primary hues, with the exception of magenta, the result of mixing red and blue hues, which are non-adjacent. The juxtaposition of red and blue is outside the visible spectrum of light. Thus, magenta is considered an extra special hue. The visual sensation of magenta is evoked by natural objects, for example fuchsia flowers, but the dye used to create the sensation thereof was only invented in the middle of the 19th century and began to be used by artists at the end of the 19th century. Light waves of extreme lengths are perceived as correlated hues, which is why connecting the ends of the spectrum produces an abstract yet consistent model called the hue wheel. In this model, there is a space for magenta, which turns out to be the keystone of the wheel. Technical language describes hues based on their position, in degrees, on the hue wheel. When different amounts of the three pure primary hues are mixed, their equal parts combine to produce the sensation of a neutral grey hue. This hue reduces the sensation of intensity. The degree of intensity and purity of a visual sensation is called saturation. All the samples produce a sensation of the same hue, but with different saturations. These are not sensations of different hues, but of different saturations. The hue is still the same, red. Light has no saturation. Saturation is a visual sensation occurring in the brain. If light waves stimulate the three types of cones equally, the signals they send evoke the sensation of an achromatic grey hue in the brain. Light of balanced composition is generally referred to as white light. Hues, brightness, and saturation cannot be seen separately. A human being always experiences a comprehensive sensation, which is composed of a hue, brightness, and saturation. This comprehensive sensation is called a colour. Colours of the same hue and saturation, but of different brightness. Colours of the same hue and brightness, but of different saturation. Colours of the same brightness and saturation, but of different hues. Hue, brightness, and saturation are the parameters of colour. Although in everyday language we simplify things by saying that light has colour, hue, brightness, and saturation, we must keep in mind that this is just a mental shortcut of turn of phrase. Indeed, clearly defined terms must be used in scientific and technical language. The perception of colour is a subjective experience, but that does not mean that every person sees colours differently. Apart from cases of visual impairment, most people see colours, i.e. respond to light, in a similar way, as they share the same psychophysiological structure. In order to research the perception of colour in a systematic way, the International Commission on Illuminance, CIE, introduced the concept of a standard observer. The human eye can see with the entire surface of the retina, where light-sensitive cells are distributed unevenly. The eye simultaneously receives a great number of signals that produce sensations of different colours, all of which influence each other. In the centre of the retina, there is a sharp central vision pit, i.e. the fovea, in which there are only cone cells sensitive to wavelength, i.e. hue. It occupies 2 degrees of the viewing angle. With the viewing angle being limited to such a small and very sensitive area, researchers have been able to standardise and reproduce sensitivity measurements of an average healthy human eye. In 1931, the definition of a 2-degree standard observer was introduced, in which the colour sample occupies 2 degrees of the vision angle, thus corresponding to the size of the fovea. In 1964, the lesser-used definition of a 10-degree observer was introduced. In colour matching experiments, a standard observer adjusts the ratio of RGB components until they get the sample colour to match the displayed reference colour. The human eye does not see anything but light. Light can reach the eye from objects that emit light. These objects are called light sources. Light sources include fluorescent tubes, light bulbs, candles, and also all types of projectors and computer monitors. A computer monitor is actually a flat lamp illuminated by millions of crystals. However, light can also reach the eye indirectly, i.e. after being reflected from an object, re-emission. When we think that we can see an object, we in fact just see the light reflected from it. Light illuminates the objects from which it reflects, which is why we call it an illuminant. Light and illuminants are not the same thing. Objects absorb, re-emit, and transmit light to varying degrees depending on its wavelength. The degree to which light of different wavelengths is reflected is illustrated by a re-emission curve. Note, the concept of re-emission pertains to a diffusion reflection from an ideally matte or opaque surface, where the principles of specular reflection do not apply. Objects act like filters which absorb component waves of the incident light. An object illuminated with neutral light, which absorbs the red component, reflects green and blue components, which when mixed, these components create the perception of a cyan hue. An object illuminated with neutral light, which absorbs the green component, G, reflects the red and blue components, which when mixed, make these components create the perception of a magenta hue. An object illuminated with neutral light, which absorbs the blue component, B, reflects the red and green components, which when mixed, make these components create the perception of a yellow hue. The names cyan, magenta and yellow are used to describe the colours of triad printing. An object illuminated by neutral light, white light, which absorbs and reflects all three components in equal measure, is perceived by the human eye as having an achromatic colour, i.e. grey. An object which entirely reflects the natural light components at full brightness is perceived by the human eye as white. If an object absorbs all incident light, the eye will not see anything. A black colour therefore indicates the absence of light. Black is darkness. If we can see anything at all, then we are certainly not seeing black. In the model presented, hues result from the subtraction of components of white light. This is why we call it the subtractive model of hue creation. If we perceive an object as red, it means that the object reflects the red component and absorbs entirely the green and blue components, which together produce the cyan hue. The reverse is also true. An object perceived as being cyan absorbs the red component. Such pairs of hues are called complementary hues. Complementary hues are located on opposite sides of the hue wheel. By covering objects with certain filters, we can give them different abilities to absorb and reflect light waves. These filters are called paints, inks, toners, pastels, gouaches, etc. Whatever the name, technique or ingredient, they always serve the same purpose: to filter incident light. In printing, the degree of filter emission is regulated by breaking the filter into smaller fragments and by covering the substrate, paper, transparency or printing foil, with it to varying degrees. The grid of different sized dots creates what is called a raster. Paintings, regardless of their content, is always a combination of light filters applied using different methods: brush, spatula or splashing. There are only two methods for creating colour: additive for glowing images and subtractive for illuminated images. Whereas the subtractive method is consistent with our life experience, as everyone has mixed paint, a description of colour using RGB numeral values is not intuitively imaginable. Various colour models corresponding more to practical applications were therefore established. A colour model is a set of parameters presenting the method of their creation and definition. There are 4 colour models. Trichromatic model. This model is based on the sensitivity of cones to light waves of varying lengths, and on the method for determining the composition of light that reaches the eye. It is based on the theories of Thomas Young 1802 and Hermann Helmholtz 1850 and is a model of complementary colours. Tetrachromatic model. In the tetrachromatic model, photosensitive cells are sensitive to the strength of light, which determines the perception of brightness, and are stimulated or inhibited by pairs of opposing colours, red-green and blue-yellow. The opponent's colour model was created by German physiologist Ewald Hering in 1892. Colour perception model. The third category of model describes the characteristics of a colour sensation in parameters corresponding to its mental interpretation, namely in terms of hue, brightness and saturation. This category includes Albert Munsell's model of 1905 and the HLS, HSB, HSV, etc. models used in computer techniques. Full model. The fourth kind of model combines the parameters of mental experience with the parameters of the light evoking it. The CIE Lab 4-colour model of opponent colours was established in 1976 out of the CIE XYZ trichromatic colour model of contemporary colours created in 1931. The parameters of colour make up the coordinates of a theoretical space encompassing the set of all possible colours in a given colour model. This set is called a colour space. The CIE lab space is a space that covers all colours. It is device independent because it includes all colours distinguished by the human eye. Each device and technique for creating colour can store or create only a limited number of colours. For example, all monitors create colours according to the RGB model, but monitors of different classes can display different ranges of colours. Each printing technique creates colour according to the CMY model, but the limit value of a neutral colour or white is determined by the colour of the paper under the layer of ink. This restriction is not due to the colour model, but to the specifics of printing techniques. The same image printed with the same ink on two different types of paper does not look alike. In fact, there is no perfect ink that completely absorbs light components, and the 3 CMY filters applied do not absorb all the light or produce the sensation of a deep black colour, but rather a very dark grey colour with a brown hue. Therefore, in printing, an additional black K-key filter is applied. The separation of RGB colours into the CMYK colours is a separate issue. The colours that can be seen on a good monitor screen cannot be printed, for example in a newspaper, which strongly absorbs the ink, thus reducing the colour saturation. The set of all colours that can be stored and displayed on a particular device, depending on the colour model, device parameters and materials used, is called a gamut of colours. Each colour model, technique of colour creation and device has its own colour gamut. The gamuts of colour space of various devices and technologies differ qualitatively and quantitatively, which means that either the colours of one gamut do not fall within another gamut, or they do not have an exact match. Gamuts are usually compared with reference to a device-independent lab space. The aim of reproducing images is to make copies of colours identical to the originals. Until recently, the most common originals were analogue images to which copies could be compared. Nowadays, originals are much more often digital files, based on which each device reproduces an image with colours that fall within their gamuts. Because the gamuts of the devices do not overlap, perfect colour reproduction is not possible. Yet it is possible to reach an optimal reproduction, matching the best equivalents of the colours of one gamut to those of another gamut, matching the best equivalents of the colours of one gamut to those of another gamut. Colour management is a technique used for optimal colour reproduction. Colour matching is used to monitor the performance of this technique. The input material in colour management is a digital file with RGB color parameters of the images created in computer programs or analog images digitalized with a scanner or a digital camera. The final product is an image created with devices operating in different color spaces and with different gamuts, which is shown on various monitors and RGB displays and printed using different printing techniques, CMYK or hexachrome. Color Management System, CMS, consists of a Color Management Module, CMM, and color profiles of devices and techniques used to create color. In 1993, several leading companies in the computer industry established a consortium of color, ICC, International Color Consortium, which introduced the most popular standard for color management. Color profiles are tables assigning colors from the gamuts of specific devices or color creation techniques to their optimal color counterparts in the color conversion space, independent of those devices, Profile Connection Space, PCS. The color profiles are made for specific devices, device types, and standardized techniques of color creation, displaying and printing. Based on the profiles of devices, the CMM Color Management Module recalculates the parameters of color from the gamut of the input device to the color conversion space, and then from the color conversion space to the gamut of the output device, based on the chosen display method, the rendering intent. For more information, see the film on color management. Profiles and colorimeters cannot see color. The same image can evoke sensations of different colors, as a sensation depends on the properties of the image and the sign of an individual and changing illumination conditions. Color matching is used for the final assessment of color quality. Unlike technical devices, the human eye can experience optical illusions, which can change the appearance of a color depending on its surroundings. Samples viewed separately have uniform shades of grey and are treated as such by colorimeters and profiles. When directly compared, the same samples look as if they were darker when viewed against a brighter background and brighter when viewed against a darker background. Red fields have identical parameters, RGB 22000, but the human eye sees them as different colours, lighter and darker, depending on the background. This difference is not accounted for by either meters or colour profiles. It can be seen only by the human eye. More precisely speaking, colorimeters measure correctly and the human eye sees correctly. However, colorimeters do not measure colour itself, but the light components reflected from the surface at a particular point of the sample. The brain, on the other hand, produces a colour sensation while being stimulated by the eye cells that see the sample and the other cells that see the background. Humans accumulate a memory of natural colours, such as skin colour, the colours of the soil, fruit, grass, water, etc. Thanks to this colour memory, humans are able to verify the reliability of the colour reproduction made by the colour management system, even without seeing the original. Colours have a myriad of shades, but a human being can easily recognise a plastic lawn or artificial flowers. The human sense of vision can recognise the colour of objects, even if the stimuli reaching the brain should evoke the sensation of another colour. This ability is called chromatic adaptation or colour constancy. For example, we know that strawberries are lying on a white plate, even if they are illuminated by warm light of the setting sun or the cold light of a fluorescent lamp. Chromatic adaptation refers to the fact that the human brain remembers colours, and when observing an object in a particular situation and under particular light conditions, it subconsciously accounts for adjustments to its colour. However, chromatic adaptation does not work when we observe images instead of objects under changing light, illumination conditions. The image is a separate object. The colours of the object that we perceive depend not only on the ability of the objects to absorb various light components, but also on the composition of the incident light. An object which absorbs the red component and is illuminated by balanced RGB light is perceived as cyan. RGB minus R equals GB, which equals C. The same object, absorbing the red component R and illuminated by light with no blue component, i.e. yellow light, RG, is perceived as green. RG minus R equals G. The same object absorbing the red component R and illuminated by light without the green component, i.e. magenta, RB, is perceived as blue. RB minus R equals B. Even slight variations in the hue of light mean that the same objects illuminated by different lights are perceived as having different colours. The differences are particularly apparent in the case of neutral colours, grey colours. An idealised physical body that absorbs all incident electromagnetic wavelengths is called a perfect black body. The model of a perfect black body is a hole in a sealed cavity with walls that totally absorb the incident wavelength. The Sun is a nearly perfect black body. A perfect black body at any temperature above absolute zero emits electromagnetic waves with a continuous spectral composition and above 1000 degrees Kelvin, also visible radiation, light. Together with an increase in temperature, the maximum spectral composition, black dots, moves towards the short waves. This means that the average hue of the light moves from red to blue, from a hot colour to a cold colour. The hue temperature is the temperature of the black body at which it emits light with a particular hue. Each light has a hue resulting from its spectral composition, which can be described by RGB parameters, as our sense of vision turns the effects of various wavelengths of light into an RGB tri-stimulus. Because the hue and spectral composition of illumination affect colour appearance, copies of the image should be assessed using the same light conditions under which the original image was created. In 1931, the International Commission on Illumination, CIE, introduced the concept of a standard illuminant, i.e. a light with a typical spectral composition. A basic A illuminant has a spectral composition of light emitted by a perfectly black body with a temperature of 2856 degrees Kelvin and corresponds to the composition of a typical household incandescent lamp. Illuminants B and C result from filtering an A illuminant to simulate various phases of daylight. B. Colour temperature of 4874 degrees Kelvin. C. Colour temperature of 6774 degrees Kelvin. The F-type series is characteristic of fluorescent lamps. F1 to F6, typical lighting. F7 to F9, broadband lighting. F10 to F12, narrowband lighting. In 1964, the CIE introduced the D series of standard light, daylight, characteristic of natural light. D65 lighting is an international standard of average daylight in Central and Northern Europe. Introduced in 1974, D50 lighting, with a colour temperature of 5003 degrees Kelvin, is used to assess colour in the graphics industry. The CRI Colour Rendering Index, scale 1 to 100, is a lightweight parameter that specifies the degree of similarity between the colour viewed in the test light and the colour viewed in the reference light. Comparisons are made for a set of 8 colour samples with low saturation, 4 samples with high saturation, and 2 samples of typical colours. The first 8 colour samples are used to calculate the averaged RA ratio. This index was created 40 years ago to assess the quality of fluorescent lighting. In 2010, the US National Institute of Standards and Technology, NIST, developed an alternative to the CRI index, called the Colour Quality Scale, CQS, which is primarily used to assess LED lighting. The assessment is carried out on the basis of a set of 15 colour samples with higher saturation and a broader palette of red colour than in the CRI samples. Producers of the new generation of LED light sources assume a daylight colour temperature of 5,600 to 6,000 degrees Kelvin. Uniform conditions for the visual evaluation of colours, colour matching, in the graphics, print and photography industries was defined by ISO 3664 from 2009. Below are the most important recommendations for the lighting of workspaces. Standard lighting, D50, 5,000 degrees Kelvin. Intensity, 2000 lux, plus or minus 500. Natural environment, chroma, less than 2. Colour rendering index, CRI, greater than 90%. The Lettero colour control system can be used for devices intended for use in all industries where colour is an important feature of the product. For example, printing, photography, ink production, textiles, plastics, building and decorative materials, the food industry, exhibitions, museums, industrial design, etc. All Lettero devices meet the requirements of ISO standards. The new line of Lettero devices uses the latest LED light sources. For Lettero devices with conventional fluorescent lamps, we now offer new light sources in the form of standard dimension tubes equipped with LED modules. For more information, visit our website www.lettero.com.pl.